Everybody's got to do this online in class. There are 4 questions. All right, let's look at these. First off, what does this symbol mean? Or this symbol. Very good. So for the first one, hey, we have, what is that squiggle thingy? Negation. It's a not. And it's called a tilde. It means not. It means it's in mathematical, it's the negative sign. Basically, what this is saying is if we had a number and the negative of that number, that's what it's telling us. So, how many rows are we going to have? By 3. First off, you can't have 3. You cannot be an odd number of rows. It has to be an even number. So what do we title the first column? P. What's the second column? And the third column is that. We have to, this is how, remember mathematics, you build up to it. That's what you have to do with these truth tables. You have the statement. So first off, the only letter you have here is P. You have to start with that. Then in this sent paragraph, you have a not P, so you need that in there. Now you got to put them together. So what are the possible outcomes for P? True or false? That's all. So not P would be what in this first one? And the other one? So true or false is false or true is. So that's when this statement is always true, because if you have a number or not that number, so if you have 3 or not 3, that's always going to be true. If I'm thinking of a number, it's either 3 or not 3. You can't miss it. So that's the first one. The second one we have, and how do you read that one? P and Q. So what are our columns going to be? How many columns do we need? Yeah, we need 1 for P. We need 1 for Q. And the statement, P and Q. How many rows? 4. Because P can have true or false. Q can have true or false. So there's 2 of those and 2 of those. So there's 4 possibilities. Now, I've been looking at you guys brought me these solutions. Keep your logic the same way. Make your truth tables, the beginning parts, make it the same. So what can be the possibility of these first 2? True and true. Then true and false. So now this one can't be true anymore, so it can be false. This one could be true, false, and false. Keep it in some logical order where it's always the same. Because I saw some students turning stuff, it's always mixed up. Yeah, it's not wrong. It's just that if you do that, then you can easily get confused on what you have to do from each column. So, and if it's true and true, true. True and false, false and true, false and false. Why are these false? What picture did we use? cylinder, yes. If you had, because this is an and, that means this first switch and the second switch have to be in a row. So if they're both open, the water comes out. If one of them's closed, then water doesn't go out. If one of them's closed, or if they're both closed, that's the easiest way to look at those. That's for the and statement. Then for C, we had, and that's the what statement. This is the or statement. Again, since we only have two possibilities, this is two possible outcomes, so there should be four possible outcomes. We need one column for the P, one column for the Q, and one column for the P or Q. So they're both true, true, false, false, true, false, false. And this one was like the goalpost. If I have a switch here and a switch here, and I put water into both of these. If they're both open, will water come out? Yes. If one of them's open, will water come out? Yes. If one of them's open, if they're both closed, no. That's the easiest way to think about it. What's a paradox? No, it's true and false. It was, yeah, I'm seeing if, but that's perfectly safe. It's a statement that's both true and false. Why can we not use or? Because if it's or, it's always or. I mean, all of these, the answer could be true or false. It doesn't mean anything. But if the answer is true and false, that can't be true. That's never true. So who now thinks they got 100? Missed one? Missed four? So yeah, don't worry about. So please, get ready by reviewing your notes. If we ever have any quizzes in the future, it's always going to be only of the day before. Only. I'm not going to throw any trick questions ever. I'm always going to give you just straight up stuff we did in class. What I'm going to use these things for, they're going to be grades, but I'm going to take all your quiz grades at the end of the semester and add them together, divide by 10, and that'll be your bonus points. Where were we? Oh, as opposed to a paradox that's always true and false. A tautology. You never heard of that. This is a statement that is always true. Now, here's what it says. When you read something like this, what this means, when a statement is always true, That means the end result, the last column, is always true. For example, like this one, P or not P, it's always true. So this is a tautology. This is a tautology because the outcomes are always true. These are either true or false. True or false. But a tautology is always, in other words, if you do your truth table and the last column is all trues, that's a tautology. That means it's always true. No matter what you do, it's always going to be true. All right. Remember this from algebra, distributivity? What is the distributive property? In algebra, the distributive property looks like this. Where you have a number in front called a coefficient. The distributive property combines both addition and multiplication, because everything else in math has to be separated. So what would this become? What do you do with the distributive property? Right. Whatever the coefficient is, since it's multiplied, you multiply it to every element inside the parentheses. Because if you can't do the parentheses, what's inside the parentheses, you have to get rid of the parentheses. This is how you do it. So we have ax plus ay. You've seen this in math before. In logic, they're called De Morgan's laws of logic. Remember, everything in mathematics had to come from this, has to fit the philosophically logical constructs. So we have two of them. De Morgan's laws. It says this: P and Q. Have you ever seen 3 equals before? These are called logically equivalent. What do you think logically equivalent means? Here's an example of logically equivalent. Logically equivalent means if I did a truth table on this side and I did a truth table on this side, the answers would come out exactly the same. So if you do the truth table, you get the exact same solutions. That's what logically equivalent means. And we'll prove that in a second. So what this thing tells us by using a distributive property, I distribute this to every element inside there. So the not, so I get not P. That's the first one. How about not and? What's not and? So it becomes an or. And then we have a not Q. There you have the distributive property. I know, pretty cool. This started thousands of years ago. So that's with the and statement. We also can do it P or Q is logically equivalent to what? Very good. Not P, not, or it makes it and not Q. So it just sounds more impressive if you say De Morgan's laws of logical equality or laws of logic, as opposed to distributivity. So let's prove these. Let's do two. Let's do two. Let's do truth tables for these guys. Which one? You want to do the first one or the second one? Which one looks more fun? Yeah, we're both gonna get the same logic in both of them. So let's look at the first one. We have P and Q is logically equivalent to that. So let's create truth tables. So what's the first column going to be? No, the first one, we have to build, remember, rules still exist. You have to do inside the parentheses. What do we need? We need a P. We need a Q. Then we need a P and Q. And then we need a not P and Q. You have to build your logic table. So we have true, 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 false, false, true, false, false. So in the next column, P and Q, what is this one going to be? True and true is true. True and false? False. False and true? False. False and false? False. We just did the inside parentheses. Now we got to do the not P and Q. So what's not T? Not F, not F, and not F. There. You have to build it slowly. So here are our solutions for this first statement. Let's do the same thing here. So we need P, we need Q, so what else? What's the next column? We have P and Q. Nope. Not P. We have first do not P. Then we have to do not Q. Then we have to do not P or not Q. You see how we're building this up? We have to find P, then not P, Q, then not Q, and then put them both together. So we have true, 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 false, false, true, false, false. Now you see why it's important to always keep the same logical pattern of your first two columns, your P and Q, because that way you know what you're looking at. Any table you look at, you don't have to decipher what is it, true or false. You know, first row is always going to be true, true. The last one's always going to be false, false. So what's the next column going to be? Yeah, it's not P. P is true here, so it's false. Then it's false. Then it's true. Then it's true. That's P. Now let's look at Q. Here's Q. So not true is false. Not false is true. Not true is false. Not false is true. Because now I have both of these pieces built. Now I can put them both together. So I look at these two columns for this answer. False or false is false. False or true, true. True or false, true or true. So now, are these two columns equal? Yes. They're logically equivalent. What do y'all think? Make sense? Makes sense when I do it. But again, once you walk out that door, you'll forget it all. But now we're going one step back further. Where do P and Q come from? Let's look at it. Here's how you would normally be getting an example. It is rainy or it is Monday. That's a statement. Here's the word or, so what symbol do we put there? So this whole sentence here is my P. So P represents it's rainy. This, I define it as Q. It's Monday. So from here, I put it together. So true, true, true or true is true. True, false, true or false is true. False, true, false or true is true. False, false is false. So this is how I took this. We have to first convert the statements as a variable and the operations as a symbol. And then we have to put them together in our statement. What do these mean? So if it's rainy or if it's Monday, true. Those are my conditions. If it's rainy or if it's not Monday, does it satisfy this condition? Yes, because it's an or statement. If either of these are true, the whole thing's true. If it's sunny outside and it's Monday, is that a true statement? Yeah. If it's sunny and Tuesday, is this a true statement? No. So that's how you break it down. What do you think? The next topic. Conditionals. Have you ever heard of conditionals before? Yes, you have. You grew up with it. Didn't your parents, mom or dad or whoever, your teacher say, if you don't clean up your room, you can't go outside? if you don't clean your room, then you can't go outside. That's a conditional. A condition has to be met in order for it to work. We call these if-then statements. If this is true, then this is your reward. So if we have some sort of hypothesis, then some conclusion. That's a conditional statement. Another one we can look at that. It says, if this occurs, so if P occurs, if that's true, then it implies that Q is going to occur. Because here's my P, this is my Q. If P occurs, then Q. This symbol here means implies. So if this event occurs, then this event's going to occur. We have truth tables for those as well. So whenever you have an if-then statement, you have to use that symbol. It's not and or, it's a conditional. So let's look at P, if P, then Q. That's how you'd read this. If P, then Q. That's how you'd read this. So we have our P and our Q, and then we have if P, then Q. Because it's a conditional, we can't use that water thing anymore. So we use a valley. Up here is where you want to be. Think of the business world. This up here is success. This down here is failure. So if I start off here and go here, is that a good thing? If I start at success and I end in success, is that a good thing? Yes, so that's true. If I start at success and go to failure, is that a good thing? No. If I start at failure and go to success, is that a good thing? Yeah. How about if I go to failure to failure? It is a good thing. If you start a failure and go to failure, have you lost any ground? No. It's only bad is if you lose ground. So that's why the only thing that's a F is if you do this. If you go from high to low. Anything else is a good deal. If you stay where you are, that's not a bad deal. In Vegas, they said, as long as I break even, I'm doing good. As long as you break even, it's not a bad deal. The way I look at it is if I'm breaking even in Vegas, I'm getting a free vacation. The only time I lose money is if I start off with $100 and end with nothing. That's not fun. So that's the if-then statement. Let me see. If the sun is shining, then the pool is open. That is just a traditional one. That's if P, then Q. Here's my if statement. There's my P. Then here's my Q. If the sun is shining, the pool is open. Do they mean the same thing? Why not? Because here's the if statement. It means it's conditional. Whenever you see the word if, that's a condition. So what this says, if P, Q. They mean the same thing. I just don't have to put the then there. It's implied that it's that. Because if this is true, comma, the pool's open. The pool is open if the sun is shining. Is that the same thing? Is that a conditional? Yeah. The pool is open, comma. So that's Q. If P. You don't always have to start off with P. You can look at the condition, and then here's the conditional. The pool's open. That's the conclusion. If the pool's open, yes. I mean, if it's sunny. D. The sun is shining. The pool is open. It's the same thing. So what this says is P implies Q. The sun is shining, that's P. The pool is open. Think about it. If you said it's after 6 o'clock, the movie theater is open. Or it's 7 o'clock, the show is starting. That's the same thing. Since it's 7 o'clock, that implies the show is about to start. Even though the if then part is not stated explicitly. That's D. How about E? The sun is shining. Oops. Shining. If the pool is open. Or only if, should that mean. The sun is shining only if the pool is open. P only if Q. Think about it. When are pools open? When the sun's shining. So if the pool's open, then we know it's what? Sunny. So we say this, it's the sun is shining only if the pool's, it's not necessarily a necessary condition. Can the sun shine in the wintertime? Is the pool open in the wintertime? No. But during the summertime, if the sun is shining, then we know the pool's open. It all means the same thing. The sun is shining is a sufficient condition for the pool to be open. What does sufficient condition mean? Yeah, that's enough of a condition to open the pool. The sun is shining, so P is a sufficient condition for Q. All of these mean the same thing. It's just they're written differently. The pool being open is a necessary condition for the sun to be shining. Remember, if the sun is shining, then we know what's going to happen. The pool's open. So the pool is open. If the pool's open, what do we know for sure? Then it's got to be sunny. So it's a necessary condition for it to be sunny. So even if you don't even open your windows, if you live in the basement or inside in the middle part of a hotel, if you call the swimming pool, they said you call the front desk, is the pool open? And if they say yes, what do you know is going to happen outside when you go there? It's going to be sunny. So without ever knowing anything else, it's a necessary condition that the pool being open will tell you that the sun is shining outside. So Q is a necessary condition for P. Those in parentheses, so separate them. So all of these refer to the same statement. It can be written, so there's if I give you a statement, even if you don't see if then, you know it's still going to be a conditional. Because these are all subsets of conditionals. It's a necessary condition, it's a sufficient condition. So far, so good. So yeah, look at each one of those. It's just that now, when you're taught to read, when you read mathematics or any scientific stuff, it's different than when you read for English or history. When you read for English, you just want to know what the general idea is. What's the story about? But when you read for science, technology, engineering, you have to read specific. What does all this stuff mean? The same as in law. If you read a case, you have to know what each word means, how they're related. All right. So what does that symbol represent? Implies. So this statement has three related implication statements. So whenever you see, how would you read this? If P, then Q. Or P implies Q. If you have that, now we have three other statements that we can go along with it. So here's our statement. P implies Q. There's our statement. We can look at the converse of it. Now, I don't mean the sneakers. The converse of that statement is if Q, then P. So what does converse mean? Flip. As opposed to the inverse. What is inverse? The opposite. So what would be the opposite of this statement? What was that? It doesn't apply, yes. But now how do we put that in symbols? No. If we do the other way, that's where this one is. Because if we change the arrow going this way, then we have the converse. The inverse is completely opposite. So if not B, then not Q. So basically, you take the inverse as a negation of the original statement. If P, then Q, then if not P, then not Q. Converse is just switch P and Q. Contrapositive. Contrapositive. Ever hear that word before? Contrapositive, this is all you need to disprove something. Contrapositive is one instant where it's the opposite of the truth. So you notice how converse was the flip of the statement? So the contrapositive is going to be the flip of the inverse. If not Q, that implies not P. Yes, for our quizzes, you have to know these. Example 6. Here's a statement. If I am in Dallas, then I am in Texas. Find these four statements for me. So what's the first thing you have to do? What's the statement? What is the statement? What do we have to do? Are we going to keep on writing everything? What's that? Not comma. Because remember, it's an if-then statement.
So if P then Q.
Very good. If P, then Q. Very good. Yes. Because it's an if-then, we use the implies. So what's the converse of this statement? If Q, then P. Which in other words is what? If I'm in Texas, then I'm in Dallas. What's the inverse? Right. So if I'm not in Dallas, then I'm not in Texas. Is that a true statement? No, you could be in Fort Worth or San Antonio. And the contrapositive? Yeah, so not Q, then not P. So if I'm not in Texas, then I'm not in Dallas. Make sense a little bit? I'm not gonna lie. I mean, it seems easy, but you can always make very, very small errors that'll go a long way. Okay. If a number is a natural number, the number is not zero. So I want to know the statement, the converse, the inverse, and the contrapositive. So what's the statement? Very good. Very good. Because what would Q be? Because Because there's a not here, then it says if P, then not Q. So the statement of Q would be the number is 0. Since it says not 0, we have a not Q in there. Very good. So what's the converse? Very good. If not Q, then P. Inverse? Very good. In mathematics, if you have two negatives next to each other, what does that equal? What happens to those negatives? They cancel, we get a positive. Same thing with logic. The two negatives cancel. So if not P, then Q. Then actually it would be if not P, then not Q, which is Q. And the contrapositive? If Q, then not P. Very good. So far, so good. Let's look at the first and the last ones. Do they mean the same thing?
Yeah, I think so.
Yes. Yes, they will. Thank you. Good job. Theorem 2 says the equivalence of a statement and its contrapositive. What this thing says, the statement is if P, then Q. What this thing says, it's the equivalence. It's a logical equivalence to its contrapositive, which would be not Q implies not P. Let's create a truth table for this. How do we prove logical equivalence? The truth table of this one has to be the same truth table as this one. So the last columns have to be identical. So we have P and Q. So it's going to be true, 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 false, false, true, false, false. Then we have to prove if P, then Q. So true to true, if T, then T, that's T. If T, then F, F. If F, then T, T. If F, then F, very good. So these are my answers. I'm hoping that the other side is going to be the same. So we have P and Q. So it's P, T, 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 F, F, T, F, F. So what's the first thing I got to build in my column? I'm trying to prove this side. I have to do not Q. So the first thing I do is prove not Q. So if Q is T, what is not T? F. If Q is F, then it's T. If it's T, then it's F, and it's F, it's T. So we have this one. Now we gotta do the other side. We have to do the not P. So if it's P is T, then not T is F. If it's T, then it's F. If it's F, it's T and T. Now we can put these two together. If not Q, then not P. F and F, true. T and F, false. F and T, T, T and T. So this and this are identical. So it's logically equivalent. Makes sense? This is a lot of extra work, but we have to show that it works. So those were conditionals, if-thens. Now we're going to look at when we say equals in mathematics. So if I said that x equals 3, then two things have to be true. X equals 3 and 3 equals x. If you ever took chemistry, you learned stoichiometry. The equal sign is really this. The left side has to be the same as the right, and the right side has to be the same as the left. We call this bidirectional. And instead of doing that, we use that symbol. So we can say that that's just a solid way of saying that P and Q are the same thing. Now, how do we prove this mathematically? What we have to do to prove this, we have to look at if P implies Q and if Q implies P. That's what equality equals. This is how we prove this. Thanks. Bless you. It's bidirectional or biconditional. Why is it biconditional? Because here are the conditions. If P then Q, and if Q then P. So it's both directions. So instead of writing this, we just write this. Valid reasoning. Ever hear of Venn diagrams? So that's when you have the circles where they overlap and stuff like that. So this is group A, and this is group or set A and set B. So what does this one tell us? It says all of set A, set A is in set B. So what this means is this. All A are B. That's how you would read that one. Here's set A, and here's set B. How would you read that one? No A are B. Here's set A. Here's set B. What does this represent? Right. Some A are B. And then lastly, we have here's A, here's B, and we're looking at these numbers. Because some A's are B. This one says some A are not B. If some A are B, then some A's are not B. These are the only possible combinations we can have when we deal with Venn diagrams. So how would you draw? Here's an example. All dogs are animals. How would you draw that in a set category? Yeah, so here's dogs and here's animals. That's true. So all dogs are animals. So Goofy is a dog. So what can you conclude? This is my hypothesis. So my conclusion is Goofy is an animal. Why is this example so good? Is because a lot of people think in Disney, you have Pluto, you have a Goofy. What's the difference? Is Goofy a dog? Yeah. He's got big ears, he's got a tail. But that's not part of the conditions. Are there any animals that can speak? Birds, parrots, actually, and dolphins and gorillas that can be taught to speak with sign language. Yeah, last example. If a person is healthy and a person eats cereal, then what can you conclude? Then what? If a person is healthy and they eat cereal, what can you conclude? If they're healthy and they eat cereal, okay, so you say that P, this is P, and this is Q. Can you also say that the cereal, if somebody eats cereal, then they're healthy? Are you sure? Because if a person's healthy, they eat cereal. So if they eat cereal, they got to be healthy. Is that not a true statement? Or if it, remember the way, if you can find me one example where it's not true, then that ruins it. That's a contrapositive. So this is people who are healthy eat cereal. So are people who eat cereal? Are there any unhealthy people who eat cereal? Yeah. People who just eat meat. Some of the greatest athletes in the world, the marathon runners, come from Africa. They don't have cereal. So they're some of the most healthy people in the world. They could run forever and not have a high blood pressure or heart rate. So, are there people who are healthy that don't eat cereal? Yes. So this is not a true statement. Are people who eat cereal, there are people that don't eat cereal, are they healthy? Yes. So both of these are false statements. Because if you can find one example where it's not true, it's thrown away. Because we're looking for validity here. Is Pluto a dog? Is Pluto an animal? So, yes, so all dogs are animals and Pluto's a dog, so he's an animal. How about Mickey Mouse? Is Mickey Mouse a rodent? Are rodents animals? So Mickey Mouse is an animal? Yeah, don't say that in Disney. You'll get strung up real quick. So yeah, that's it for that section. So that's 2.1 homework. You should do that now. Next time, we're going to look at more about sets. Okay, everybody, have a great day. Have a great weekend.